Okay, my name is Philip Di Melo, and today we'll talk about a fundamental problem in public health epidemiology. And I will show you how to solve this problem in a very easy way. Okay, uh, that problem is, we can formulate this problem is the probability of an infected person in a population with, let's say, infected person, let's say in flu, is 1/100. Okay, so this is an average probability. What is the size of the population group that at least one person is infected with flu with a probability of 99%. So it is almost 100% that you will encounter a person with flu in this cohort, in this group of people in this community, for example. But an average is 1/100. So what happens is that usually people say that, oh, it has to be 100. Okay, but this is not true, because we know that if you take, let's say, a die, and the probability of having, let's say, 1 is 1/6, right? Let me just write it here. Okay, so if you take a die, probability of having 1 on a die is 1/6. So it is not true that when you toss the die 6 times, you will absolutely sure that you will see one, at least one. It is not true, because when you do this experiment, we have, let's say, can be 2, can be 3, can be again 2, can be 6, then will be again 6, it's again 6, then will be 5, whatever. You can go on and on and on, and you won't see one. And we call this theoretical probability. And this is experimental probability. That's exactly what happens when we do, let's say, experiment. And this is the same thing when you do epidemiological experiment. It is not necessarily true that if a theoretical probability of flu, let's say, is 1/100, when you take 100 people taken from randomly from the community, it is 100% you will you will meet a person who has flu. And this is not true. And this is a fundamental theorem, fundamental problem of epidemiology. What is the probability? What has to be a size of this group of people that with 99% has 1 or 2 or 3 people who are infected. It's same thing when you look at this problem with die. You can say what's the probability, how many times you have to throw a die to get at least one. This one, to get it at least one time, right? So this problem actually can be formulated in a very simple way. And this is quite known solution. So if, for instance, we take P of A, it is at least 1, you will see infected people in the group that you have chosen. It is called probability. We can put it as P small. And P with a bar, it means that in this group, you won't see this infected person or infected people, you won't see them. We call this Q. Okay. The same when you talk about the die, the probability you see 1 is 1/6, but the probability that you won't see 1 Okay, so we will call it as P1 with bar equals 5/6. Okay, so now what happens is that this problem has a solution. So this problem says that this probability of having, let's say, one person infected or two people infected, we can express in terms of Bernoulli formula, which is this one. Bernoulli formula is this one, where P is finding a person, Q is not finding a person, and what we have to find is the number of people in your group that guarantee that this person will be here. And CKN, this is a binomial coefficient, n factorial over n minus k factorial, k factorial. So k is a number of successes. So the number of people that we will meet if they have flu. It is not, of course, success, but it means the success of that you encounter them in this group. Okay, so that is this formula Bernoulli we call. And this is quite a simple formula. We can see, for instance, what the probability is that we have k or two people. So instead of k, we have to put 2, and the problem will become C binomial 2n, and we have to find P2 Q to the power n minus 2. And what happens is that actually this is where n is unknown. We have to find it. So the problem is this is a probability to find, let's say, 2 people. We can put like this: 2 people infected in the group, and n is unknown. What happens is that when we work with Bernoulli, it always gives us problems with computations because n can be 10,000, 15,000, and it's not easy to calculate all these things. Plus, we have to calculate the probability to have 1, 2, 3, because we want to know at least one person. It can be 2, it can be 3, and so forth. And so it shows you some complexity. I will show you now how we can solve this fundamental problem in just a very, very simple way, absolutely simple way. So the idea of how to solve this fundamental epidemiological problem is not to solve this problem, but to solve a problem which is complementary. We will find the probability that we will not see in this group infected people. Okay, so in this case is k equals 0. K equals 0. Okay, so when k equals 0, okay, that this problem can be much easier. But the problem is that we also do simplification because we know that when we talk, actually in public health, always we do this because we have lots of, we talk with populations, with public and so forth, so n can be big. And for this we have a very, very accurate, in this case, so-called Poisson approximation. Poisson approximation. So now we solve this problem with k equals 0. So we don't want to see infected people in this group of people that you have chosen. So in this case, the Poisson formula becomes very simple because lambda, I will tell you what does mean lambda. Lambda is n that you don't know times the theoretical probability. We have it is 1/100. So lambda we know. So the problem is, if we know n, of course. So when k equals 0, then we have that lambda to to the 0 power is 1, and k factorial equals also 1 when k equals 0. Yeah. So the problem is that this one term becomes 1, and we have just a formula. We have, let me just erase this, what we don't need. Okay, so this is second. Okay, it doesn't matter. So we have just e to the lambda power, which is e minus lambda np. So we do not know n, but p we know it is 1 over 100. It's theoretical probability we know. So theoretical probability said that the probability average to have this situation flu in society is 1 over 100. So, and this equals not 99%, because 99% was for the direct problem, but for the supplementary problems that we do not see will be only 1%, right? Because 199 minus 99 is just 1%. So we have, instead of calculating all these situations with different probabilities and with very large n to find out, what we have to do, we reduced all this problem into a very simple thing. It is e n to the over 100 equals 1%. And what is 1%? It is 0.1. That's it. So now we have to find n. N is very simple because we apply natural logarithm to this equation. It will become right away minus n over 100, because logarithm e is 1, equals logarithm 0.01. So logarithm 0.1 will give you negative 4.6. Negative, you can cancel out, and you multiply by 100 both parts, and you have n equals 460 people. So what does it mean, this number we received? We received that this number, that if you take the group that consists of 460 people randomly chosen in this population, with 99% of probability, you will find a person in this group who is infected with flu or other diseases. It depends on what kind of probability you have. This is a very important and fundamental problem of epidemiology, and I just showed you that this problem can be solved in just I don't know, just writing this formula and calculating it without doing anything, And this problem is considered to be complicated, difficult, and so forth. So I showed you that this is actually very simple, and you can solve. This is similar to this. We can solve anything, other problems very easily. For example, if you have probability 1 over 200, let's change it. And you want to find not 99%, but 95% of probability that you will find in this group of people at least one who is infected and who, let's say, presents just a challenge to the health of the community, for example. So it is very, very simple to do this. You can write, you can surprise your colleagues, because you can write the solution right away. the solution is that you have to solve the problem e minus power n that you have to find over, now not 100 but 200, right? 200 equals not 0.01 but 0.05, because you solve a complementary problem. In the direct problem was 95%. In the complementary, it has to be 5%, because 5% plus 95 is the gives you 1. Now, what you do, you apply logarithm to this both sides, and you have n equals negative 200 times logarithm point 0.05. Okay, so you just look at the table to find logarithm, and you can see right away this formula, how you can accurately identify this, calculate this number of people in your group that you have to choose to have at least one person is sick. Okay, so instead of doing lots of calculation, as usually we do in digital epidemiology, we have many calculations. These problems, we can write away the answer. The answer is this one: n equals this number defines the probability of, it's 1/200. It's a probability, it's theoretical probability of having this disease in the population times this probability of the supplementary program. Don't put here 95. It is supplementary. It has to be 0.05. And you can take these tables, in the online. You can see right away this group. In our case was 460. Okay, I think you just understand this, and you can use it in your work if you deal with this problem, similar problems, or problems that contain these calculations. All right, thank you, and bye-bye.